Okay, so confidence intervals for means. I want to estimate the overall population mean, but I can't ask everyone, so I take a sample. That sample mean is called X bar. That sample mean is called X bar. X bar is the sample mean, and it's an estimate of the overall population, right? Hopefully my sample mean is representative of the overall population, but sampling is random. What if my sample mean was too big or too small? There's some error. I want to create an interval where I have some level of confidence, some level of certainty that I've captured the overall population mean. So let's add and subtract the appropriate margin of error. What's the margin of error? Minus the margin of error. Within this interval of values, I have some level of certainty that I've captured the overall population. The margin of error is how many standard deviations I have to add and subtract so that I have some level of certainty I've captured the overall parameter. Since we're talking about small sample sizes, typically sample sizes that are less than 30, because as you saw on the graph, for sample sizes of less than 30, there's a difference between the t distribution and the z distribution. We're also using unknown parameters. Instead of having the population standard deviation, I'm using the sample standard deviation as an estimate. So our margin of error is that t-score times the standard error of x bar. The standard error is an overall estimate of the sample standard deviation. Look up your critical t-score. That tells you the correct number of standard deviations that capture a certain part of the distribution. Take that t-score times the standard error, which is an estimate of the overall sampling standard deviation. Back in our previous standard, standard 17, the standard deviation of the sample means is sigma over root n. But we're using unknown parameters. I'm using the sample standard deviation as an estimate. So therefore, this is called the standard error. And an estimate of that standard deviation of our sampling distribution is S divided by the square of that sample size. This part of my formula is called the margin of error. It is the maximum difference between my estimate, x bar, and the actual population parameter I'm trying to estimate. So here is our formula. Overall, the confidence interval for small sample sizes, for small means, is our estimate plus or minus the margin of error. That margin of error is how many standard deviations, that t-score, times the given standard error. The standard error is an estimate of the, an estimate of the sampling distribution standard deviation. Standard error of x bar is S over the square root of that. Of course, your handy dandy formula sheet has all this written down for you already. Look at your formula sheet, guys. I'm looking right here. I should also say that the degrees of freedom. Is that -1? Whoa. Take a sample. The sample mean is an estimate of the overall population mean. I also add and subtract the margin of error, so I have some level of certainty. I've captured the overall population parameter, the population mean. All right, let's put this into action. The Super Bowl is this Sunday, and most NFL stadiums actually use lighting that's produced right here in Iowa. There's a company called Musco Lighting, based out of Oskaloosa, that lights up a lot of college and pro stadiums around the country and world. So Musco is testing a new model of light bulb to use at sports venues. After randomly sampling 12 bulbs, they find an average lifespan of 8.3 years and a standard deviation of 1.7 years. What is a 95% confidence interval for this scenario? Sampling can be very expensive. Take a lot of time. We're talking about 8.3 years of time to get that average. They're not going to want to test 50 different light bulbs. That probably costs too much money. So they're going to take a smaller sample, but small samples have more variability. So we need a t-distribution to make this confidence interval. What is our sample size? Well, it's less than what number? N is 12. So therefore my degrees of freedom is 11. Okay. What else we got? 8.3 years. Does that refer to all the light bulbs or some of the light bulbs? Is that the population or the sample mean? They find it sample mean. It's the specific lifespan for the 12 bulbs in question as a part of our sample. So this would be X bar. I'd expect all bulbs to also have a similar lifespan, but maybe they don't. There's some variability involved here. That's what's accounted for by the margin of error. This standard deviation is the sample standard deviation, S. I'm using the sample standard deviation as an estimate of the overall population standard deviation by an unknown parameter. We need to do a 95% confidence interval. Let's use that to look up our t-score. Let's use that to look up our t-score. %, which means there's 2.5 in either tail. Look up your t-score chart. What's the t-score that captures 95% of our distribution? We have 11 degrees of freedom, so I know I'm in this row right here. We have 5% error, or 2.5 in either tail. So what is that, as we practiced earlier? 2.201? Is that right? .201 standard deviations above and below the mean capture 95% of the distribution. Pause here. Did everyone find that okay on their t-chart? Use a t-chart to look up your critical t-score. Cool. All right. Here's our confidence interval. Sample mean plus or minus the low. Sample mean plus or minus our t-score times the standard error of S over root n. Let's see. 8.3 plus or minus 2201 times 1.7 square root of 12. Catch your breath. Beautiful. Let's first figure out, we have the plus or minus. What is the margin of error? Did I get that typed in right? 1.08. So my sample estimate, my sample mean of 8.3 years is no more than 1.08 years away from the actual average lifespan of all of these light bulbs in question, right? Let's take our estimate of 8.3 plus or minus the mo. By subtracting the margin of error, my left endpoint is 7.22. When I add this on, I'll have the right endpoint. And 38. Of course, these are no longer proportions. These numbers have what units? Here's. Let's label them accordingly.
How'd you do that part again? How'd you get the 7 point?
I did up on the screen, Jack. I took I just added and subtracted the margin of error. I took the plus or minus, right?
The margin of error was not for the
This is the margin of error right here. It's the correct number of standard deviations that we have to add and subtract to capture 95% of the distribution. Good question. What does this mean in context? Let's interpret our confidence interval.
I'm 95% confident that the actual lifespan is between the average lifespan is between 7.2.
Sounds reasonable. I usually start with my confidence level. 95% confident that the lifespan of the bulbs is between 7.22, 9.38 years on average. This is a confidence interval for the average lifespan. So somewhere you have to use the word average. We are 95% confident that the average lifespan of the bulbs is between the two endpoints of our confidence interval, 7.22 and 9.38. The word average has to appear somewhere in your confidence interval. The average lifespan, we are 95% certain, is between those two endpoints. Okay. On the back wall behind Nora, you got one to do before you come. We'll do some more practice tomorrow. When I was driving to school this morning, I hit the train. So this popped into my head as I was thinking about good examples this morning. Well, I had to stop for the train. Interested in traffic patterns here in town, the local police department wants to know the length of wait times at the train crossing. After sampling 25 random drivers, they find an average wait time of 72 seconds with a standard deviation of 8 seconds. Create and interpret a 99% confidence interval for the data. Should be approximately what I have on the board in red. 99% confidence interval. What is the sample size? 5. What is X bar? What is our estimate of the average wait time? And our sample standard deviation would be 8. Obviously, look up the correct t-score. Determine your margin of error. Then take X bar plus or minus the level. Formula should be on your formula sheet, as well as on this board. The other side of the room. Let's see. 24 degrees of freedom. See it? Good. 2797. Yeah. There we go. Look good. 99% certain that the average wait time is between 67.53 seconds and 76.48 seconds. For drivers here in Denver.
Are you on the paunch? I have to read it.
Yes.
I have seen your meeting.
This is absolutely right. This is absolutely kind of.
They find only like 3 minutes, like different.
I missed one slide. I missed one slide.
He said that like asked what he said. Oh yeah, I still have to include my pictures.
Missed one slide by 1 second.
You guys? Yep.
Two.
Let
Here, I'll.
Chris, Maya, how we coming, guys? As we're wrapping up in class here.